everyone, it's Ms. Chun with some video solutions to the day 25 Lewis structure practice. So just as a reminder, the point of drawing Lewis structures is a way to represent molecules that involve all nonmetal atoms that are sharing electrons. So we're basically representing different types of covalent bonds. So we're going to use dots and lines to show which electrons are being shared and also which valence electrons end up being non-bonding around these different atoms. So not all bonds have to involve a complete transfer of electrons. In the cases with nonmetals where their electronegativity values are a bit more similar, they can also share electrons in order to gain a full octet or a duet in hydrogen's case to become more stable. So for the first example with hydrogen fluoride, HF, we're going to first look on the periodic table to find the total valence electrons. So hydrogen is going to have 1 valence electron, fluorine will have 7. So we're going to have a total of 1 plus 7. We're going to have a total of 8 valence electrons available to distribute for bonding within this molecule. So we're going to arrange it with an H and an F. We don't have to worry about a central atom since there's only 2 atoms total. And then just so you can kind of visualize it, we know that hydrogen is going to have 1 valence electron to start, and then fluorine will have 7. 1, 2, 3, 4, 5, 6, 7. But if they share their electrons, hydrogen will become stable with a total of 2 valence electrons, and then fluorine will also become stable with a total of 8 valence electrons, and that just depends on them sharing a pair of electrons. So if we translate from the dot structure to the structural formula, every shared pair of electrons is going to be given one line, one shared bond, and then all of the unshared, all of the non-bonding electrons will just stay as dots in the structural formula. Okay, so there we go. That's the example for HF. Next, let's do it for silicon tetrafluoride. So we'll learn how to name these in another lesson, but let's take a look at the valence electrons for silicon. It's in the same group as carbon, so it's going to have 4 valence electrons. And that's why things in carbon's group, like carbon and silicon, will want to make 4 bonds, since they're going to want 4 additional valence electrons to complete their octet. Fluorine, like in the last example, will have 7 valence electrons, but this molecule has 4 fluorines, so we'll multiply that by 4. And we'll have 4 plus 28, we'll have a total of 32 available valence electrons for us to distribute in this molecule. So in this case, we are going to have to determine the central atom, since we have a total of 5 atoms in this molecule. You can look, and sometimes the one that's listed first will be the central one, just because that'll be the only the single sort of lone atom, and the rest of the atoms will go around it. You can verify it though, because the least electronegative atom will be in the center. Electronegativity will increase as you go from left to right and from the bottom to the top of the periodic table. So fluorine is our most electronegative atom. Remember, the noble gases aren't going to be involved in our bonding discussion since they're already stable. Okay, so silicon's less electronegative than fluorine. So we're going to put silicon in the center, and we're going to kind of form like a box-like formation around it with these 4 fluorine atoms. And then the first thing I like to do is I like to place 2 electrons between the central atom and each of the atoms surrounding it. And then I like to complete the octet for each of the outermost atoms. So I'm going to put a total of 8 electrons around each fluorine. And then let's see how things stand with our total valence electrons. So we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. So you have a total of 32 valence electrons placed in this diagram. We had 32 available valence electrons. Let's just double check that each atom has a full octet. The fluorines look good. And then the silicon atom has 8 around it as well. So it looks like we're in good shape. So let's go ahead and translate this into our structural formula. So each shared pair of electrons gets turned into a single line. And then all of the unshared electrons will remain as dots. And so each fluorine will have 6 dots remaining around it in the structural formula. Okay, so there's our solution for the second example. For the third example, we have nitrogen trifluoride. So we're going to take a look at the periodic table. Nitrogen has 5 valence electrons, and then fluorine again has 7. So we're going to do 5 plus 3 times 7, which will give us 26 valence electrons. So nitrogen's going to be less electronegative than fluorine. Nitrogen's also the sort of the lone atom in this molecule, so we know we're going to put nitrogen in the center, and we're going to put 3 fluorines around it. Let's start off by putting a pair of shared electrons between nitrogen and each fluorine, and then filling in the octet for each fluorine. Okay, then let's kind of make a quick count to see where we're at with the valence electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. We have 26 available. Nitrogen needs 2 more, so there we go. Looks like we'll be in good shape if we put those last 2 next to nitrogen. Let's double check the octets. Okay, each fluorine looks like it has 8 valence electrons around it. And then our nitrogen also has a total of 8 valence electrons around it, so we're in good shape. Let's translate this into the structural formula. There will be a single bond between each nitrogen and each fluorine, or the nitrogen and each fluorine, excuse me. And then each fluorine will have 6 unshared electrons. And then in this case, our nitrogen will also have a non-bonding pair of electrons next to it. You'll learn about this later, but that non-bonding pair around the central atom does affect the overall geometry of the molecule, but that's something we'll discuss after spring break. Okay, and then finally, let's take a look at this last example. So this last example is going to be a little bit more challenging, and I'll show you why. Let's first find the total valence electrons. We have 3 carbons. Each carbon has 4 valence electrons. So 3 times 4 plus, we have 6 hydrogens. Each hydrogen we know has 1 valence electron. So 12 plus 6, so we have 18 total valence electrons to distribute in this molecule. Now we know that hydrogen will never be in the center since it can only share a total of 1 pair of electrons, and it'll only want to make 1 bond. So let's go ahead and put the 3 carbons in the center. So this one's a little bit different because we kind of have like sort of like 3 central atoms. I guess that 1 carbon is technically the central atom, but we're going to line up those 3 carbons next to each other first. And then just to start off, let's try to evenly distribute the hydrogens and see what happens when we do that. Okay. And then I'm going to draw a pair of shared electrons between each central atom and its surrounding atoms. And let's see where we're at now. We have 2, 4, 6, 8, 10, 12, 14, 16. We only have 18 valence electrons, and these 2 end carbons are still missing 2 electrons to complete their octet. So if we were to put in those 2, we'd be over the available valence electrons. So we'd have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. We only technically have 18 available valence electrons. So here's what I'm going to propose we do for this example. I'm going to erase one of the hydrogens in the center carbon, and I'm going to bump that hydrogen to the end here. Okay, but then what's happening here is that this central carbon now only has 6 valence electrons around it, and then this end carbon on the right has these 2 just sort of floating on the end here. So what if I put these valence electrons on that end carbon, I now made them shared between this end carbon and the middle carbon. So let's double check the count now. 2, 4, 6, 8, 10, 12, 14, 16, 18. So that works if we form a double bond between 2 of the carbons. So we still have a total of 6 hydrogens and 3 carbons. And then let's double check that each atom is stable. So remember, hydrogen is happy with a total of 2 valence electrons. So let's double check that each hydrogen is stable. Okay, that looks good. And then each carbon is going to want 8 valence electrons around it. So this far left carbon is stable. This middle carbon is stable. It has a total of 8 electrons, 8 valence electrons around it. And this far right carbon has a total of 8 valence electrons around it. So we're in good shape. So let's go ahead and translate this to the structural formula. So we're going to have a carbon here with a single bond to a carbon there, but then these last two carbons are going to share a double bond, and then each hydrogen is going to have a single bond to its nearest carbon. Okay, and that is what our structural formula will look like for C3H6. There are no dots in the structural formula because none of the electrons ended up being unshared. So all of them were involved in a shared bond. Now, some of you may have ended up sort of like reversing the double and the single bonds for these N carbons. So if you end up kind of doing like the mirror image of this, where you put the double bond between these first two carbons, and then you let this last carbon have the single bond with 3 hydrogens, that's totally fine. Either answer would be acceptable. So there we go. That's your video solution to the first part of the day 25 homework. Thank you for listening.